Hello, everybody. My name is Mohamed Elsersy, and I am presenting our research work titled Privacy Preserving Data Sharing Scheme for eHealth System. This work was done in collaboration with the University of Southern Mississippi and our team here at Higher College of Technology. So let's start by our agenda for today. So I'll give a brief introduction about what we are doing and then define the research problem that we are working on and give a short description for our general architecture. And then I will mention the design goals that we hope to achieve and demonstrate the proposed method by giving a brief overview and initialization of the system that we are working on, and how we will encrypt the patient data and match the patient encrypted data. Then this will be followed by performance evaluation regarding the security and privacy analysis. And then I will list some of our experimental results, describing the experimental setup, the detailed result, mentioning the competition overhead and scalability results. And then I will finalize by giving the conclusion of our research work and the future work that we may have. So first, we are dealing with the patient record. Most of these records now are found in electronic format. They are called the electronic health record, EHRs, which is very vital for the modern medicine right now. The accessibility and the portability of these records is very important. Also, the ability to share these records among the service provider and doctors is still needed, and it may help regarding the telemedicine that may be needed in the future. Still, the patient confidentiality and the data integrity is a primary concern. Thanks to the cloud service provider, which are now the primary source for sharing these records. But this still needs secure storage and to ensure the confidentiality of that stored record. So our research problem is defining a privacy-preserving data sharing scheme for eHealth systems. Because each record are detailed account of patient information. These are generated by health care providers and distributed among various sections or even facilities. So in this paper, we are trying to find a way to secure the data sharing, encrypted data search, and privacy aware and preserving for these records. Here I may remind you with one incident that happened a few years ago for a movie star in Hollywood. And this actor, George Clooney, has a breach where his medical record was leaked to the press in a big scandal at this time. So this may be a very harmful for celebrity and also for any person. So protecting against the attack is a big deal. This is why we will use encryption. In our general architecture, we have the key distribution system that will give keys to be used using the key nearest neighbor classification. And our patient will encrypt and upload their EHR records to the cloud server. And now patient and doctor can also query these records. The cloud server can search the data and return the requesting party. In this figure, it shows here in the middle, the key distribution center, where first the patient upload the record. This can be done by patient or doctor. And then there is an encryption for the queries that comes from both sides. And this statistic goes to the cloud server. And then we will have the search and the recover process that will happen after this queries comes. So our design goal here is, first, patient can share their records with multiple doctors, and patient can search over multiple doctor encrypted records. Doctor can search also their patient record that's encrypted. There is unlinkability of these encrypted queries. And also we need to handle the scalability problem when this record goes to grow much. Our proposed scheme is to achieve this privacy-preserving data sharing scheme. So our scheme goes through the initialization of the system before it starts to work. Our players here are patient, doctors, cloud server that will receive their keys from the KDC. And the patient will be able to encrypt and upload their health record to the cloud. During the stage, the doctor will build a set of indices from their patient health record. Doctor will be able to create encrypted authentication, and the encrypted queries are sent to the cloud server, where the cloud server can search over the encrypted health records using the KNN method to find the record and match the query. Here is the initialization of the system, where we will have a security parameter as an input, and this will be sent to the KDC to generate the secret key, where it has also a random binary vector of length scale and set of random invertible matrices. The KDC will create the cloud server secret key, which it has an invertible random matrices. Each doctor will build a set of indices extracted from the doctor patient health record. This index is created by invoking the create index function. For each medical record data, the doctor will use the secret vector generated to split the indices into two columns of the same size, and the doctor will use its secret key to compute the medical record data of that one. The cloud server will use KNN method to search over the encrypted data to find the patient record that match the doctor request. In this scenario, the cloud server should first use its secret P-1 to remove B from that record. So let's look in the performance evaluation for that method. We analyze the security and privacy, where we have the KNN scheme provide patient privacy preservation by having the EHR is encrypted barrier to the upload. Once it's uploaded, searchable by either patient or doctors. All records are held together but distinctly differentiated. They are held on the cloud server. This server is the exclusive access point to the data. Queries from doctors and patients have no personal identification. We have the splitting function to introduce controlled randomness to the queries and the data that will increase the security. For internal and external attackers, internal, it will be honest but cautious, so don't disturb the flow. External, no index keys, no significance query can be met. Let's look into the experimental result. First, I will talk about the experiment setup. We used a computer occupied by Intel Core i7 1165 G7 that works with 2.8 gigahertz processor, and it has a 16 gig RAM, which is a regular computer everybody can reach nowadays. It's occupied with Windows 11 professional operating system, and we use the Spider IDE as our development kit. Our program scripts were written using Python programming language version 3. We utilize scikit learn NumPy machine learning library. We generated random of 84 bytes test data files, statically code the quantity of records generated in library. Random query generator determine target files for both doctor and patient tests. Each encrypted file has a size of 11.88 kilobyte, same size for encrypted query. Both are used by inferring similar data and statistic in their respective Bloom filters. Searching takes the dot product between the query and the file is a maximum similarity of 1. This table lists the competition overhead. First, the time taken by program to generate index key for doctor and patient. The average time was 0.733 milliseconds. The time taken to generate an encrypted query, the average time was 0.148 milliseconds. The time required to perform search for one record over one patient, this was 2.378 microseconds, which is very small compared to the 2 previous times. Regarding the scalability, we have recorded the total encryption time in seconds for data files being encrypted starting by 1 file and going up to 400 files. We see a linearity that exhibits the scheme are able to encrypt at a constant rate, even if the data file number increases. Also, we recorded the encrypted file library volume and the total encrypted search time over library measured in milliseconds here. And we see there is an exponential growth that exhibits the statistical increase of searching longer body of files. In conclusion, to summarize what we have done, we have proposed a scheme that was able to achieve all our design goals as we have defined it. We employed the KNN, key nearest neighbor, on the cloud server to be able to search over the encrypted data. Patient and doctor were able to request and receive correct electronic health record within short retrieval time. In the future, we are planning to expand our work by testing it on real data files, if available. We will simulate the cloud server, upload and search, and we will do the selection and design for the KDC. We will have some real-world implementation, and we are planning to build a marketing campaign to sell this as a solution or app for the health service provider. This is one of the references that we refer to. For the full detail of the references, please refer to the full copy of our research paper. Thank you for listening, and I would like to thank also our partner in this work, the team from the University of Southern Mississippi. Here is my contact in case of you want to communicate with me after this presentation for more detail or questions. Thank you for listening.